To calculus 3. This time we are moving to section 6.3, conservative vector fields. And indeed, we are going to discuss one of the most important theorems in mathematics. That's a fundamental theorem of line integrals. So before we start, let's review a little bit about the curves and the regions. Remember, a line integral, it is the integral over a curve. So we really needed to look at the curves in different situations. And also, we already covered the double integrals, right? Double integral is the integral over region in the xy plane. And we have type 1, type 2 circle regions. And also, we are going to take a look at the different situations of regions. Okay. So first, it's about the curves. This is a curve, pretty random curve. And this is a simple curve, and it is not closed. Those two ends are not connected. And next one, it is a simple curve. Still, it is a simple curve, but it is closed, right? It forms a shape here. And third one, it still has, it is closed actually, but anyway, you see the curve to one somewhere in the, well, I don't know, somewhere in between, it does cross over itself. So it's considered not a simple curve. It's not a simple curve. And by the way, it's worth to mention, we basically, the line integral, we are going to consider the line integral over a simple curve. And could be a line integral or a simple on a simple and a closed curve. And the last two cases, these are not simple cases. This is not a simple, not a closed, the fourth one, okay. And then also in terms of regions, we do have the concept of simple connected regions. The first three, these are simple connected regions. These are simple connected regions, okay. And part B, these are connected regions, but anyway, they are not simply connected. You see, somewhere in the middle of the region, there's empty part. And in this case, there are two empty parts. They are connected, but not simple. And also, we do have the case, two regions are not connected at all. Well, it's these two together, they are considered one single region, so it is not connected at all. And again, for our purpose, and including the type 1, type 2 region we covered before, basically these are simply connected regions. Simply connected regions. Okay. And we're talking about line integrals. A line integral, it is the work done. In physics, it can be considered the work done by a force field on an object moving along a curve. And also remember the force field. Sometimes the force field, it turns out to be the gradient of a scalar valued function. Could be two-dimensional, three-dimensional functions. Gradient in the two-dimensional case, gradient in the three-dimensional case. And if that is the case, the vector value function turns out to be the gradient of a scalar valued function. Then we say the vector valued function, it is conservative. It is a conservative vector field. And also we call the scalar valued function is a potential. And it's not accurate, but anyway, I just want you to know, if you have any confusion about potential, roughly you can consider potential, it is the antiderivative. It is the antiderivative. All right, and the gradient, that's a vector, and the gradient is about derivative, that is from the scalar valued function. So roughly we can consider this f as antiderivative. Roughly, potential, it is comparable to antiderivative. Okay. And also another issue is how do we know, given a vector field and without knowing the scalar valued function, how do we know it is conservative or not? And well, for the sake of our class, we are really only looking at the two-dimensional case. So there is a simple criterion you want to consider, the so-called cross-partial derivative property. Okay, and when we have vector field, if vector field in a two-dimensional case, so P and Q, then for the P, you calculate the partial derivative with respect to y. For the q, you calculate the partial derivative with respect to x. The reason we call this as a cross partial derivative, hopefully we see this p, it is along the x direction, right? Q, it is along the y direction. So accordingly, we calculate the cross partial derivatives, dp dy, dq dx, and if the cross partial derivatives are the same, and then we know for sure f must be conservative. F must be conservative. For example, when we have a function f of x and y equals 2x plus 4y, and well, kind of very simple conservative, very simple vector field. And also, how do we know if it is conservative or not? What I did here is I calculated dp dy. Keep in mind, p now it is a function of only x only. So with respect to y, the entire thing is constant, derivative is 0. Q, it is a function of y only. So with respect to x, the derivative it is 0 again. So indeed, it is conservative vector field. And also, I just want to point out here is we do have the potential function for this conservative vector field. Give a try if it would make sense to you. F of x and y equals x squared plus 2y squared. Then accordingly, the gradient is that given vector field, right? So I said f of x and y, the scalar valued function is a potential. And roughly you can say is an antiderivative. Antiderivative of the vector field. All right, these are really not new material. That's all about for reviewing. And now let's get to the real business for section 6.3. It's a general conclusion for the line integral when the vector field it is conservative. It is called as the fundamental theorem of line integrals. Okay, and first, let's clarify a curve. Piecewise curve, well, a piecewise curve you can consider as a simple curve. And also, we could have the situation, look at the the edge of the shape. This is a piecewise curve. And I think roughly you can consider this as a piecewise curve too. And the boundary of this region, it is also piecewise, okay. That is what we mean piecewise curve. It has to be simple. Okay. And then it says when you work with the antiderivative of a conservative vector field. Remember, this gradient of scalar valued function, it is a vector field, right? So really, it is a line integral. Okay, line integral vector field, and the vector field it is a gradient. And if that is the case, really, you can consider this. You don't need to bother all the vector calculations. What you need to consider here is you work on the scalar valued function, evaluate the scalar valued function at the upper bound, t equals b, upper bound of the curve, okay? And minus the same scalar valued function at the initial point, t equals a, taking the difference. This is really the so-called fundamental theorem of line integrals. I say this is really comparable to the fundamental theorem of calculus. Remember, in the fundamental theorem of calculus, we have the antiderivative of, well, the integral of a function. It turns out to be the difference of the antiderivatives. And really the same situation. Now, when we consider the line integral, as long as the vector field it is conservative, and then we calculate the difference of the potential functions at the end and at the beginning. That is the fundamental theorem of line integrals. How about let's take a quick look at one example. It is the example in section 6.26. we want to evaluate a line integral. Okay, f of x and y, it is 2x plus 2x and 4y. And indeed, this is the same factor value function as we mentioned a moment ago. And we want to calculate the line integral. And C is the line segment. The curve, it is a line segment from the origin to point 2 and 2. I suppose that would be easy enough. Okay. Evaluate a double integral f dot dr. F is given. Curve, it is a line segment moving from the origin to 2. So what I did, first I used the definition to calculate the line integral. This is a two-dimensional vector field, right? And so accordingly, the line integral turns out to be p dx plus q dy, p dx plus q dy. And then, well, p, it is 2x. I put 2x there. Q, it is 4y. Actually, this is y, not a full pq dy. And then don't take it for granted that there are two integrals. It's a single one combined together. I mean, you cannot say x is running from 0 to 2, y is running from 0 to 2. X and y are related. X and y are not related, okay. So the next part, what I want to consider here is, well, you want to consider the parametrical equations of the line segment. Actually, I wrote the parametric equations for this line segment in the very beginning, which really means x is 2t, y is 2t. So what I did for this line integral, p dx q dy, I replace each x with 2t, each y with 2t2, and dx, it is replaced with d2t, x is with 2t. So really, this is another 2dt. dy, it is d2t2. And then I realized, even though I may have dt 2 times, but anyway, it is really a single integral in terms of t, right? T is running from 0 to 1. And this part of calculation, 3 to 2 times 2 times 2, 8t. And second part of calculation, 8 times 4 times 2, that's 16t. And dt in the end. It's a single line integral in the end. Single line integral. Single, actually, a simple regular integral in terms of t only. So hopefully you see the number here. All right. 8 plus 16, that's 24t. Antiderivative is 12t squared. So that's 12. The line integral, it is 12. And this is what I called using definition. F dot dr is p dx plus q dy. I did a calculation. Remember, in this section, really our task, it is the fundamental theorem of line integrals. So let's take a look. The calculation using the fundamental theorem of line integrals. Okay, according to the fundamental theorem of line integrals, it says the line integral here is the difference of the potential function at the upper bound at the lower bound. So what I have here is because the function, well, the vector field, it is we just covered earlier, 2x plus 4y. And I suppose you still remember the potential, it is x squared plus 2y squared. So the potential is given too. And I hope you agree with me. The calculation turns out to be a lot easier, right? F dot dr, it is the gradient dot dr. So it is the difference of the potential function. At the upper bound, 1. At the lower bound. At r equals 1 and f, well, this r of 1, because the curve, it is given as 2t, 2t, 2 and 2. I think I just figured out this really should be 2 and 2. 2 and 2. Let me see. I'm keeping this 4 here for the moment. I'll double check. I think, yeah, actually this is really 2 and 2, 2 and 2. And then the result, you plug in 2 for x, 2 for y, that's 4 plus 8. Then plug in this ordered pair, that turns to be 0. So indeed, this turns out to be 12, and which is exactly the same way as we calculate, the same number as we calculated from the definition. And also as a quick comment, even though I explained a lot, I did some actual writing, I suppose you're going to agree with me. The calculation using the fundamental theorem of line integral is a lot easier than that of the definition. So this is the first part of the discussion for the fundamental theorem of line integrals. Thank you for watching.